right. Welcome back to Physics 112. This is probably the last lecture before your exam, like real lecture. I may have to take half of the class, half of the review sessions for the lecture in case I couldn't finish the material today. Okay. So we finished last lecture with a discussion or introduction to capacitors. What is the first, any announcements from the LA? Any questions from last week? Sorry, last lecture? Good. Thank you. So we finished the discussion with a discussion or introduction to capacitor. And what is the analogy that we use? Anyone still remember? What is an analog, either fluid mechanics analog or gravitation analog of a capacitor? That's pretty good. Like my hand. The analog that we use is a water tower. So in water tower, you can store gravitational potential energy. I don't know, water tower, something like this. And then if you poke a hole, then there is fluid mechanics. There is a fluid flow, so you get energy out. Similarly, in electronics, there is a device. The symbol of the device look like this. We call that capacitor. So what is a capacitor? So water tower stores gravitational potential energy. What does a capacitor do? You guys need to just use the same sentence, replace one word. So a capacitor stores electric potential energy. So there are many pre-meds in the room. What is an example of capacitors in like classroom or hospital? Or some of you are EMT professionals. Yeah, the defibrillator. So what does a defibrillator, sorry, what does that thing do? Defibrillator. So let me. That thing right there. What does it do? Yeah, it push charges. So the question is, so for example, in this, after the class, this class, you should know a little bit more about this thing, defibrillator. This question is why we use capacitors instead of batteries for a defibrillator. I see. Good. Capacitors can be recharged, which I will show you soon. Okay, that's good. But typically in life, the answer to many questions are more than one. Even if you run experiments, some students just like this hypothesis. Turns out there are 4 hypotheses, and the right answer could be 75% of this, 25% of that. Yeah, you. Yeah. Yeah, it allows rapid release of charge. So that's another thing. It's also more stable than battery. You can also store a lot of charges. So you will have access to this lecture notes if you go to Canvas, let's say in 2 hours or so. All right, so capacitors. Have you seen capacitors like this before or no? When I was your age, it looked like this. So these are capacitors. Some of them are polarized, meaning it has positive and negative electrodes, but they come in different variations. There are many capacitors in your smartphone, in your computer. So let's revisit capacitors. So capacitors, basically, the simplest form, it has two surfaces like this. And the surface has an area, and they're separated by d, distance d. And in between, we can either put vacuum, or in many capacitors in the old days, we use ceramics. I don't know what they put these days. Okay. So let's derive the formula for a capacitor. First, let's define capacitance. Capacitance is defined as the ability to store charge, and we will discuss what this Q, in a given voltage. So C is equal to Q divided by voltage. What did I? Yeah, so I wrote this, but you can quickly rearrange to the second formula. So capacitance, or C, is Q divided by C. So what is this Q? So for example, if I charge this capacitor, so initially the capacitor has zero net charge. After I charge a capacitor, there is a net plus on one surface and net negative on the other surface. So after charging, and this is of course 2D representation, but it looks more like that. So positive on one end, let's say negative on the other end. Can you see this? Good. And you guys should be an expert for Gauss's law. So first, in physics, we often make approximation to make our lives easier or easy. We assume that these two plates are infinite. The reason why we assume these plates are infinite, so we don't have to worry about the edges. So if we have positive here, negative here, there is a net electric field, which is E. Okay. And we derived E last time to be what? Using Gauss's law, remember? We use the surface is equal to sigma divided by permittivity. There is a factor of 2 here. But since there are two plates and they point towards the same direction, the factor of 2 disappears. So let me just simplify the formula. So you add two numbers, two equal numbers, you get twice of the same number, right? So E inside a capacitor is sigma divided by epsilon naught, and we define sigma to be the charge divided by the area, the total charge divided by total area. Okay, we have done this before. The only difference is that before we only did one plate, so we have a factor of 2 here. Now we double the magnitude. And also, so this is 1. And last time we also defined, so when we learn potential and the electric field, we define that for a constant electric field, the voltage, the electric field is the gradient of the voltage, meaning the relation is the delta V divided by D. V here is V, let's say left, minus VB. So this is just, and I'm just going to say it VAB. Basically a potential difference. So we have two equations. It's good that we have Q because we can compute C if we know Q and V. All right, so So next we will use equation 1 and equation 2. We set them to be equal. So on the exam, I'm not going to ask you to derive this equation, don't worry. But it's good for you to see how the equation is derived. All right. And then Q is equal to C times V. In this case, the potential is VAB. This one, maybe equation 3. So C VAB divided by A epsilon naught. Again, epsilon naught is the permittivity of a vacuum, which is just a parameter that describe how electromagnetic field and wave travel in a vacuum. VAB divided by D. So we are almost there. So this VAB cancels. So C is equal to A. I like to put epsilon naught in front divided by D. So this is the formula that you use in homework 2, and also when you were reading Perusal. Any questions? For the exam, all you need to know is this equation for a capacitor that looks like this. Okay. Meaning it doesn't look like this. Meaning the material between the two plates, the two areas, is vacuum. But you can put ceramic in between or a dielectric material, then the formula turns to K epsilon naught A of D. Okay. Where K is just a constant that is specific for a certain material, for a dielectric material. So what is K for vacuum? Close. 1. Yeah. So if you set K is equal to 1, then you get the capacitor without the dielectric material. Okay. So let's do demo. And on the exam, I may ask you about a demo, the demo. So the formula is C times permittivity times area divided by D. So this is a capacitor. So let me switch to a different camera. And then let me switch to another camera so you can see the voltage. Enough. Apologize that it's not focused. Yes. All right, so this is a capacitor. Again, in capacitor, you can change the area, not this one. This one, the area is fixed. The distance and the material in between. Area, distance, material in between. Okay? So right now, the potential is, interesting. Why is it not 0? What? Oh. First, I need to hide my picture. Oh, like this. Well, it's okay. Okay. Why is it not? Sorry, it doesn't work. I just realized that the image is flipped. Everything is flipped. Everything is mirror. Okay. So just trust me when I say that the voltage increase or decrease. Okay. Or you can kind of see it. The camera is fairly good. So this is a voltage. It measures the potential. So right now it's close to 0 basically. This is a capacitor. So what I'm gonna do first is I want to charge the capacitor. I want to put charges. Okay. So basically what I'm going to do right now is I'm going to connect the capacitor to a battery. Are we good? Do you want to share anything? Okay. If it's too easy, if the class is too easy, talk to me after the class. I can give you more difficult derivation. Okay? We are here to help you. All right. So, and then what I'm going to do right now is I'm going to charge the capacitor. Going to charge. So basically just connect positive and negative to the capacitor. Oops. And what you see is that the voltage increases. Right now, the capacitor is charged and hold Q. So right now it has Q, and now I disconnect the capacitor from the battery. It's just standard battery. I assume 10 times 9 volt batteries. Okay. Okay. So now the voltage points to roughly 80 volts. So what I'm gonna do is the easiest thing to change is I'm gonna change the distance. So Q times V, sorry, Q is C times V, and then the readout that we see is V, right? This machine measure V. So we need to derive a formula for V. So V is equal to Q divided by C, which is equal to Q divided by K epsilon naught A divided by D. Okay. Is that clear? Can anyone see this? Oh, it's I think number 3. So this formula here is, so V is proportional to D, basically. V is proportional to D. D is the separation. And V is proportional to 1 over area. And V is proportional to 1 over K. Okay? So what happened if I decrease the distance? Somebody with a black jacket with Nike, is that Nike brand? If I decrease D, will the potential decrease or increase? Decrease, good. So I'm gonna decrease D. And what do you see? Yeah, it went down a little bit, so maybe I need to be more aggressive. It's going down. I'm not. But initially it was like this and like this. Apologize, I didn't realize that the camera mirror. So there is basically initially the voltage high, now low. Okay. So next is, let's say, so first we cannot change the area. This the area aspect. So what happened if I increase K? So what happened if I add a material in between? So K is larger than 1. Would the voltage increase or decrease? So initially K is equal to 1. If I change the K into, let's say, 10, the voltage will increase or decrease? Will decrease, right? So hopefully this one works. See? Let me. Next time, one of you, I'm gonna invite one of you to help me with the camera. No wonder you cannot see. So now the voltage goes to this one. So initially it was like this, high voltage. Now the voltage. So what happened if I remove the dielectric? It go back. It doesn't go back. I think I know why, because I accidentally touched. So the charge jump from one area, from one plate to another plate. I shouldn't have done that. Okay, but you hopefully get the idea. This type of experiments should be part of your lab, and it's a fair question for the exam. Okay, what happens if we double the area, double the separation, multiply the separation by a factor of 20, let's say. Any question? And good. Okay, so let's return to the lecture. Okay, so this is a fair question on the exam that relates to this demonstration. It's a question about capacitor, so it's an I-clicker question. With plate area A and separation D, capacitance is C. If the area is doubled and the separation is tripled, what is the new capacitance C? You can work with your neighbor. Ah, 30 more seconds. All right, so I think almost all of you have answered the question. 5 more seconds. All right, so what is the answer? So the formula is given here. The dielectric is still vacuum, so no dielectric material. So the new area is what, twice? Twice. I'm just gonna put 0 subscript there, and then 3. So I don't know how to do this. Maybe C after C prime, maybe. And this is C. Well, naught is dangerous because there is this permittivity. Anyway, we can do this. So C prime is equal to epsilon naught times 2/3 times n naught divided by Z0 is equal to 2/3 C. Okay. So the answer is C. Basically, 80% of you got it right. Any question? Easy. So on the exam, I can, instead of asking you about the capacitance, I can ask you about the voltage, or we can add dielectric materials. I can even name the dielectric materials and give you a table. You need to find the dielectric, this K constant, like this K here. Let's skip this question. Okay, we can, if you want to practice, we can do it next week. We will have 2 review sessions. Okay, so next is capacitor in series, and this is part of your perusal reading. So similar to water tower, you can put two water towers next to each other or in parallel. And the idea is by putting 2 water towers, let's say in parallel, you will increase the capacity. You will increase the number of water that you can release. So similarly, in capacitor, we can either put multiple capacitor in series. Series looks like this, or parallel. series is looks like this, and the capacitor, they don't have to have the same value or parallel. So this is in series. The second arrangement in parallel. What is the third arrangement? You can have a combination of capacitors in series and parallel. So the easiest example is just combine the two. 1, 2. So, and you can have more complex arrangements. Here there are 6 capacitors. So the question right now, this is a common problem for electrical engineering courses and physics courses is, let's say you want to build a better medical instruments or defibrillator. You may want to either connect your capacitors in series or parallel. The question is, what is the equivalent capacitor for series, and similarly, what is the equivalent capacitor for different arrangement, in this case parallel. Okay. Clear? So you read the derivation in Prusel, but we can do it in class. Hey. All right. So first, for series, we have to invoke conservation of charges, which applies to not only series but also parallel. So let's say for series, the easiest way is for 2. Let me make sure that it's the same. Okay. Your books start with 2. So we will just work with 2 capacitors, C1 and C2. Then when you charge, if you connect battery to this arrangement, then you will deposit plus Q here, minus Q here. So there is no, you don't create any charge because the sum is 0. But now you have minus Q here. So you have to have plus Q here and minus Q here. Okay? And now we can just use the definition for the capacitance. Q is equal to CV. Okay. So there is another thing. There is another thing that I need to tell you, which is the potential is, okay, sorry. So one thing that I like is using the analogy of gravity. So let's say you have 2 drops here. So the gravity, the potential is like the height. So gravitational potential is proportional to heights. So let's say you put 2 water towers here, then the sum of the height differences should be equal to the height of the battery. We will use that. This is the reason why there is this cartoon here. Okay. So let's return to this derivation. So Q1 is equal to Q2. So this one is equal to C1 times V1 plus C2. Sorry, is equal to. Okay. But V is equal to V1 plus V2. Okay. Right. And V1 is equal to Q divided by C1. And what is V2? V2 is equal to Q divided by C2. And V here is equal to Q divided by the C equivalent. What I mean by equivalent is we want to calculate a single capacitor that can replace these two capacitors. And then you can just cancel Q. So you get 1 over C equivalent is equal to 1 over C1 plus 1 over C2. So this is in terms of the exam, this is all you need to know, plus generalization. It turns out that this formula applies to any n, any positive, any non-zero n, any non-zero integer n. If there is any math major in the room. So this one is equal to 1 over, this is by induction, is equal to 1 over C1 plus 1 over C2 plus 1 over C3 plus dot dot dot. Okay. Good. Any question? Okay. So that's the derivation. To capacitor in series, this is the formula that we have just derived. So this is the simplest version of the problem. In a circuit with delta V and two identical capacitors in series, what is the equivalent? What is the C equivalent? Hopefully it wouldn't take you more than 30 seconds. So this is the formula that you need to use. Okay, 30 more seconds. All right, 10 more seconds. All right, so what is the answer? So this is basically the problem. Two capacitors, what is C equivalent? And to be exact, C1 is equal to C2, so it looks exactly like that. And basically C equivalent is equal to 1 over C plus 1 over C. But this one, you have to remember, you have to flip, you have to take the inverse of the C equivalent. So this is equal to what? What is this? 2 over C. This is not 2 over 2C. That's not the case. Just want to make sure. Are we done? No, you need to take the inverse of that. So this one, C equivalent is equal to inverse of that, C divided by 2. So when you connect two identical capacitors, you reduce the total capacitance. So that's the easiest way to make a smaller capacitor. Okay. Good. Okay. So next is capacitor in parallel. So this is like putting two water tower close to each other, or like if I have two capacitor like this, I put it right next to each other. So it looks like this. Okay. And you can think of it as it's basically you make a new capacitor, you just join two capacitor like physically together. You just glue them together. So if I have two plates, then the area will double. The separation is the same. So you can derive that by using the conservation of charge. So Q1 plus Q2 is equal to Q, and the charge is equal to C equivalent times V. So in a parallel circuit, if you connect, okay, so first, this one doesn't look like wire to you, but actually all these lines, they represent wires. And either it can have, and then the capacitors can be anywhere. What I mean by that is, let me just draw it. So this one is in parallel, of course. And one can draw it like this. This is in parallel. And I don't have to draw it like that. I can put it here. It depends on the illustrator, the artist of the book. And all of this, they have these lines, they represent wires, and they have the same voltage. So for capacitors in parallel, the voltage here and here, they are the same because they are connected by a conductor. So basically, so Q is equal to Q1 plus Q2. Okay. And Q is equal to C times V. So what I'm doing right now, I'm deriving the equation for capacitors in series, and we want to find the equivalent capacitor that can replace these two capacitors. Okay. Q here is equal to C equivalent times voltage. And the Q in the other capacitor is just C1 times V, and V are the same. So you can cancel all V, and C equivalent equal to C1 plus C2. So mathematically, it's more straightforward. And somehow, all textbooks start with series first and then parallel. But in terms of level of difficulty, if you see this kind of question on the exam, then you should do it first. Maybe I was in a good mood. Okay, so this is a sample question. So we have two identical capacitors, C. They are connected in parallel. What is the equivalent capacitance? So it's really straightforward, 30 seconds. Oh, I haven't started it? Sorry, thank you. So 3 more seconds. Good. Basically, all of you got it right. So you just sum the two capacitance of two capacitors. So the answer is 2C, right? Next is we can connect multiple water towers or capacitors in parallel and series, something like this. And it can be a lot more complex. And I will leave this as homework to you. And I'm happy to start the next class, which is a review with this problem. Is that good? Okay, so next, there is a concept of energy that a capacitor can hold. So basically, if you hold, so capacitor can store energy, as we discussed in the beginning of the lecture. So what is the energy? You can use your physical intuition. Of course, if you have more charge, then the energy should be higher, so it makes sense. If you put more voltage, then the energy also should be higher. Turns out that when you do derivation, this is the formula that you get. So Q squared divided by 2C, or 1/2 divided by C, 1/2 times C times V squared. And you can derive the second term from the first term by using the definition of the capacitance, which is Q is equal to capacitance times voltage. And then the energy of unit is, of course, joule. So on the exam, I can ask you how to calculate this energy. But one thing that one can do is, first, I will ask you to calculate the capacitance. So let's say I have 5 capacitors. What is the energy that the circuits can store? So first you need to calculate C. And then I will split the multiple option questions into multiple questions, so you get extra credit. Okay. We only have 9 more minutes. So basically, in this question, you know what? Let's do this in class because it's a fun problem. So we have 2 identical capacitors. You have 2 identical capacitors, then you have 2 choices. You either connect them in series or parallel. You want to use them to store as much energy as possible. What is the best way to wire the capacitors together before connecting them to a potential difference? So the key term is store as much energy as possible, right? And then the equation. So first you have the equation for parallel. For series is C1 plus C2, right? And then voltage is the same. Volt is the same. So what is the answer to this question? So I'm going to push this to iClicker. Okay. You can do this with your neighbors. So the energy is 1/2. Make it bigger. This is in series. This one is in parallel. So the options are in parallel, in series, or not enough information. So V is the same for both cases. Uh, 15 more seconds. Basically, all of you have answered the question. 10 more seconds. All right. Okay. Good. So the energy, the total energy, can be written as the first expression and second expression. It seems that most of you choose the second expression, which is the right answer. So what you want is you want to maximize C, and based on this, this one is in parallel. Based on this formula, or what we have discussed before, if we connect 2 capacitors, the capacitance increases. So if you increase the capacitance, stored energy also increases. Okay. Apologize that I made this time. You guys should have, it was a test to see whether you pay attention. All right, so the answer is A, and I need to add A in the answer. We only have five more minutes. I want to finish the lecture notes. The next one is there is a concept called energy density. Energy density is simply the energy per unit volume. And for this class, you will be given the formula. So the energy density is capital U divided by volume. The symbol for the energy density is small u. Okay. And it looks like 1/2 epsilon E squared. And E, you can calculate E if you know V and D. Okay. And the way to derive the equation is by using capital U divided by A times D. Area times distance is the volume. So one thing that is remarkable, maybe in 3 months or so, it turns out that the same equation, the one that people like physicists derive from studying a capacitor, is also applies to lights, let's say from the sun, from different galaxies. And from this equation, you can derive the speed of light, which I find remarkable because initially physicists just study this parallel plate capacitor, and they can derive the speed of light and can measure it very accurately. And then finally, we study about dielectric. This is the material that I push in and out. And again, the reason why the second part of the experiment didn't work because when I push in and out, I accidentally touched one of the plates, so the charge moved to the dielectric materials. So your book does a good job in explaining dielectric materials. The reason why it increases the capacitance because it retards or it modifies the electric field. So the dipoles inside this material align to electric field and counter the electric field that these two plates generates. So this is actually a good question to end. So this dielectric material can align its dipole moments based on the field. So I end the lecture with this question. So this is conceptual question that is a fair game for the exam. So liquid, like water, is actually also a dielectric materials. Your lead is a good dielectric materials. The thing that you use to write, like the mechanical pencil lead. But physicists found that the dielectric constant decrease with increasing temperature. Anyone knows why? Yes. Less or more? So remember in the second lecture and first lecture, we study that temperature is basically how much vibration of anything. So at higher temperature, the vibration is more, right? So because the vibration is more than the dipole moments inside a dielectric, they align. The way they align, they have more difficult time to align with the electric field. That's why this K, there is K somewhere, decreases with temperature. Good? Is that clear? Thank you. And this is the table of dielectric constant that you can find on Wikipedia in your textbook. And you can read about dielectric breakdown. All right, so I'll see you on Monday. Monday will be mostly review. And Wednesday will be review. Have a nice weekend.